What does the Cayley Hamilton theorem say? Looks like something pops up from nothing. We're going to see how the discussions that we are having on eigenspaces, eigenvectors, eigenbases, they kind of are connected with some results from the so-called Cayley Hamilton theorem. You have to know about this theorem. Very important. So, characteristic polynomial is this one. Are we together that this is the characteristic polynomial? Very much, not at all, kind of. Excellent. It's going to be a polynomial. True? Perfect. Let's take, instead of this stuff here, let's plug A instead of S. Okay? Let's make an example. I've got S squared plus 3S plus 2. Then I take A equals, I don't know, 0, 1, 0, 0. And then I put 0, 1, 0, 0 here, 0, 1, 0, 0 here, identity here. And in a certain sense, I get a polynomial that is a matrix polynomial. Okay? Together? Very interesting thingy. Cayley Hamilton theorem says, I take the characteristic polynomial that will be something. That's something, if I take A, this A, and I plug it in, I'm going to get 0. Did we already do the Cayley Hamilton theorem in this course? We did it.
Yes, we've seen it.
And then I might have copied it's okay, we do it.
The name.
No?
No, we said that just if you substitute the...
Okay. We see the implications. We are together. So this is the name. This implies this. Together, we don't prove it, but you kind of, it's an important thing. Perfect. What does this imply? It implies that if I take this one and I put it on the other side, I get something that looks like this one. True? What does it mean? It means that this one is linearly dependent on the previous powers. Not that this is a to the power of 0. Identity is a to the power of 0. True? A power of n is linearly dependent on a to the power of n minus 1 up to 0. Well, but then if I multiply everything by a, I get a n plus 1 is equal to this stuff here. True? We are together. I take this result as before, multiply times a everything. I get this stuff here. But this one is this stuff here. True? And I can take this one and substitute it with this stuff here. I expand a little bit, and what do I get? I get something that looks like this one. The coefficients are going to be different from before. True? Together that the coefficients are different, but in nature, this one is linearly dependent on a power of n minus 1 up to a power of 0. This is an implication from Cayley Hamilton. Do you see that this is an implication from Cayley Hamilton? And this also says, if we repeat this trick, any power from n above is going to be a linear combination, linearly dependent on the previous powers of a. Okay? Very interesting. Of course, depending on k, the coefficients are going to be different. Is it clear, this one? Depending on k, the coefficients are different, but it's a linear combination. Two, 3, 1, 0, power of 100. This is going to be 2, 3, 1, 0, power of 1 plus 1, 0, 0, 1. Combination of number plus number, this stuff here. You see it? Extremely powerful. Do you see how powerful this is? The numbers, we are going to find the numbers later on. We are going to find the numbers, but now the interesting part. I think I do the plot here. I think I might already been doing it before, I don't remember, but we do it. If I've got 2, 3, 1, 0, I can write it like this, a vector, 4-dimensional vector, true? If I was having something that was 3 numbers, 3 numbers, 3 numbers, I can write it as a 9-dimensional vector, true? Perfect. And then I have that this vector here, 9-dimensional vector, is a vector in 9 dimensions, true? So let's make it 1, 2, 3, 4, 5, 6, 7, 8, 9. This is a 9-dimensional space, R9. This is R9. A specific matrix might be this one, true? This might be one matrix with specific number, 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 number. Are we together? And then if I do this to the power of 0, I will get something else. And this to the power of 1, I will get something else. Are we together? And then I have that the powers from 0 to 8, they are going to form what? A subspace. True? And all the powers are going to be inside this subspace. Cayley Hamilton tells us that the powers of matrices, they live in actually subspaces. They are spanned by the powers. It might be all Rn squared, but it might be a subspace, and we are going to see that very often it's a subspace. How much are we together, people? 1, 2, 3. The Cayley Hamilton says powers of matrices live in the span of the powers of matrices. It's kind of trivial. I don't know. I think we are there. Okay? Questions?